For today's class, I just want to have a quick review on the chapter 3. We have discussed this in the early class, but some of the point I need to stress on chapter 3, which is on work holding, tooling system, and fit and speed calculation uh, in milling process. So can move on into the next slide. So this we will cover on the work holding system, what type of cutting holder, cutting tool, type of end mill, and finally we move on to the feed and speed calculation using the formulas. So these are the example of a clamping system or work holding system in milling. We can either use milling wise as we experience in your lab session. And beside that, we can also use step clamp. So this is more simple features or configuration, but however, when we consider using step clamp, ensure that we need to be cautious, especially during facing operation or side milling, because the collision might happen because of the obviously the clamp sit or rest on the top of the surface, and to prevent this collision, we can have using a meter by edge clamp or edge clamp system where we clamp towards uh, on the tangential side instead of vertical force. We apply on the tangential side force along the side of the workpiece. So this is your piece. So there are many options you can do, or you can use a counter bore here. Okay, you can use counter bore screw, and then you can prevent any collision during milling process. So this is some of the example configuration how we can set up using step clamp. So these are the configuration of step clamp. This consists of T-nut, clamping, clamp, riser, and this is how we set up the proper setup for the step clamp. So ensure during the setup, must make sure that the back clamp is slightly raised up by the riser block to ensure that the clamping force apply will be directly vertical on the workpiece. So do not slightly uh, avoid station where the backline is lower than the front. So ensure that the front side will be lower than the back side. And the first one, as I mentioned, you already experienced during your lab session, you using a milling vise. So in our milling vise, we have similar features like as in the slide. We have a solid jaw where this is a permanently or fixed position, and then you have your mobile jaw. You can adjust, the according to the size of your stock, and then you have your bearing surface where we will need to place a parallel bar to support your workpiece, and then you have your clamping slot there you can lock the vise on top of your table. Okay, and however um for our machine we have using a VH4 vise, so this is kind of adjustable. As you can see, you based on the figure we can see the pin here, so this pin can be adjustable. Okay, if let's say you dealing with the a smaller part, then you have to pull out the pin and then insert. We have a numerous hole here, position. So the one that we use in our lab is hydraulic vise. So we just only apply very light force during clamping. And our vise ensure that we have a spec. For the spec, we have a C max, maximum opening. So maximum opening we can handle with 175 size of your piece or stock. Mm. So when you want to deal with 5 axis part or smaller part, so version we have is a micro grip compared to the VH4. Okay, so micro grip we have teeth on top of your jaw. We have a teeth on the jaw side to provide a very strong clamping range up to uh, 14,000 Newton. So this is to ensure that the workpiece are rigid during machining process. However, the clamping range is only 0 to 120 mm, which is much lower, smaller compared to VH4 175. So this is only 120 clamping range. So if we deal with 5 edges, then we go for this one. Then for normal 3 edges, we can go for VH4. So I already explained on the work holding system. The one that we use in our lab is SK40 mega grapes or BDB shank. So the one that we have here is the length is 60. We have 90 mm length. Length actually refer from here to the uh, below surface of the or close to the cutting tool. Okay, this is L. So the dimension of the L will be input into the machine to determine the tool length. And what we do is L, okay, L, for example, this particular shank, L, if, okay, is 60, okay, 60 mm. And then we need to add with your tool uh, overhang, okay, and then you can get total length of your tool. Then you can add that numbers. You can need to input that numbers in the machine. And then beside that, we have the accessory wrench to open the cutting tool. So and then we have a collet system and we have a nut. This is nut. Okay. Inside the tool holder, we have a nuts. So the maximum RPM for this particular uh, tool holder or okay, or spindle, the tool holder, which is very impressive, about 35,000 RPM. So maximum. So to ensure that this is very low round out. Okay. And for the milling cutter, we have a few selection option to execute your project. We have end mill cutter and then we have rough mill. So the difference between rough mill and end mill is for roughing. You can see obviously we have segregate along the cutting flutes, diagonal cutting flutes. So the reason why we have this is to ensure that chip will be in shorter length, especially when we deal with soft material like aluminum. Okay, so and then another one is we have a thread mill cutter to manufacture or to mill the thread, and then we have a wood draft cutter for you want to create a draft angle, and then you have your ball cutter if you want to deal with the 3D shape or you want to make a radius at the corner. And we have a fly cutter for facing operation, and then we have a side milling cutter to cut off your workpiece. And then this is very common of you, face mill cutter, just for number of insert. And of course, beside this, we have like drilling, okay, to produce a hole. And then we have a reamer to widen the existing hole and finish the inner surface of your hole. So this example of milling insert. As you can see from the manufacturer, when you purchase the tool, you may have find the labeling side the packaging for the milling insert. So the color will be stand for the material of your workplace. For example, like P stand for steel, stainless steel M, and then for aluminum will be N. So different material of your workpiece will have a different recommended cutting parameter will be provided by your tool manufacturer. And beside that, you look at the color configuration, and then you need to decide also whether what kind of application you want to use for milling operation. Because some of most of the insert they will come with a different shape. Okay, you may find that some of them in round shape, square, diagonal, hexagon, and so on. So ours one in our lab we use this shape. Okay, diagonal shape. Okay, sorry, we use a square shape. This is the one we have in our lab, which is stronger than this diagonal shape or triangular shape. But the force exerted by using this shape will be stronger. So so if you consider you want to reduce the vibration, if you observe the vibration, then you can consider play around with the different shape of your insert. So this is for end mill. Okay, very simple. We only have one particular shape. Uh, okay, you can see we have a helical groove, and then we have cutting edges. For example, this is four cutting edges, and then we have right angle, clearance angle. So this cutting edges will be involved during cutting operation and okay along this one. So the selection of the end mill, when you want to buy your end mill or you want to use during machining, you have to refer the diameter, okay, and also the length of flutes. So especially when you want to perform a deep pocket cavity, so look at the length of flute that, that your tool can handle. For example, your pocket cavity is 40 mm, then you need to ensure that your length of flute more than 40, 41, 42 and above. Okay, so we try to prevent this during the machining. We want to prevent any rubbing against the shank. Okay, this area we call it shank. So this will ensure that you have a fine finish on your side pocket. And then for the fast cutting and rigidity, the recommended for the tips in machining, we always go for the shorter end mill with large diameter. So this shorter configuration with larger diameter will provide more rigidity and definitely less vibration. And then we have a variable helix and mill to reduce the chatter or vibration. And then you can use a cobalt powder metallurgy carbide, okay, to handle with the harder material. And to further improve the performance of the tool, normally most of the cutting tool nowadays they have a coating with titanium to improve the performance. Like you can use higher feed speed and tool life. So these are the the difference between three flutes, five flutes, and eight flute. So the idea is more flute will be result in a larger core and provide a better strength. Okay, so compared to three flute, five flute is better in terms of strength. Okay, and as a rule of thumb, we normally we use a smaller flute number for soft material like aluminium, and higher number of flutes for other material like steel and other alloy. So the reason is because aluminum tend to be produce a longer chip, so we need to allow the chip to travel through the uh, this gap. Okay, so so the idea is we want to remove the chip away from the cutting region. So if you're using this one, egg float during cutting aluminum, so chip will be stuck inside the gap, smaller gap compared to this one. And for the aluminum or soft material, normally we can use a higher feed rate and higher speed, okay, compared to other material like stainless steel. Okay, so the rule of thumb is if you want to produce something, uh, the first thing is you need to look at the material of your workpiece. So find uh, easy material for machining. So then you can improve your productivity and efficiency. Okay, this is a roughing and mill. This is a ball nose mill to produce a 3D shape. And then we have a hole making process, spot drill, countersink, combine, and so on. So we have a table for the to select the drill size. For example, you want to produce your hole is M10, okay, which is let's say 10 and then thread with 1.5 pitch. So the recommended drill to be used is 8.5, which is always smaller than your size of your thread hole. Okay, so we need to pre-drill and then finally you need to perform a tapping operation using this particular tap uh, tool bit. And fold making, let's say you want to produce a hole, you can use a reamer, finally, a reamer. So remaining stock from draining can be cleared by using reamer. And then for the tap, you have another option other than using hand tap or machining tap. Okay, you can also use thread milling. So this special tool will have slightly protrude the bottom edge of the tool. And then the beauty about this tool, you can use for numbers of the pitch. You can control it. You can edit using your cam somewhere. So this is you can produce multiple size of your thread compared to tab, which is only for one size. For example, this tab is 10 M10 times 1.5. You cannot use for the M12 for 1.5. Whereas for the thread milling, you can use for different configuration of your or size of your thread. So please go through the tool material. So the idea is your tool should be have a high hot hardness, toughness, uh, thermal shock resistant, wear resistant, and chemical stability. So this is the ideal cases for the tool. So manufacturer of the tool, they will strive to achieve this criteria of the product. So so this is a kind of you know um, comparison between the two material in terms of hardness and hot uh, hot hardness. Okay. So as we can see, ceramic will be the top performers for the cutting tool. This can handle higher piece, high hardness workpiece, and also high temperature, and then followed by carbide. And high speed steel will be the second last. So that's why I think more reasonable we use carbide for optimal condition and also costing. Okay, please go through the material. Carbide using tungsten carbide. Okay, and for the speed and fit formulas calculation, uh, normally we select based on the data from supplier. Uh, when you don't have your any data from supplier, then you have to try and error whether the your setting is It's okay or not. So you can define okay or not based on the chip color, size, the sound, and the sound of the during the machining. So all this will be based on your experience. Okay. So for example, you can when you using your cutting parameter, you can hear like loud sound or vibration, and this indicate your setting parameter is not optimal. Okay. So you need to adjust. So the best idea is somehow we start from data from to supplier. So these are the formula for cutting speed. We learned this from semester 5 in MEM 561, manufacturing process 2. And then, for the feed per tooth and okay. However, you can also use this link to calculate because this is a formula. You can use app or link to calculate the cutting speed, feed per tooth, and others. Please go through this formula yourself. Okay, try to practice this one for because this will be test for student in test one theory. Okay, these are example of manufacturer data from manufacturer Mitsubishi. Listen for aluminum workpiece. Okay, given that you're going to you prefer to cut for aluminum workpiece, aluminum alloy. See, this is aluminum alloy. So the grade of your tool is HTI 10. So this is the recommended cutting speed in metric unit. Okay, 2000. Okay, 2000. 2000. So the range is to let's say the rate given to you is optimal 2130. So the unit is surface foot per minute. This is not metric unit. So I have to convert into metric. 2000 will be 600 meter per minute. Okay. And heavy cutting, for the heavy cutting, okay, this unit is surface feet per minute. Okay, surface feet per minute. Then I have to convert uh, to metric. So come 600. You can Google the formula conversion. And normally during tests or during examination, I will use a metric unit. And for the cutting speed, given 600 meter per minute. And then for the feet, F, okay, feet per tooth, okay, refer to the next column, feet per tooth. For light cut or for heavy cut, for example, I choose for heavy cut. So recommended is for heavy cut, you can use the range 0.008 to 0.016 mm per tooth. Okay, so in this case, 0.01. So for example, I choose F 0.01 mm per tooth. So you can input this F, okay, F, F 0.0, 0.0, 0.0, 0.01, 600, 0.01, 0.01, 0.01, and then your 600, 600 meter per minute. Okay, 300 meter per minute. Okay, next, okay, 300 meter per minute, your cutting speed. So, assuming your diameter is 95 mm, now you want to calculate for spindle speed. So your spindle speed is 2011. Okay, and next, we input this figure, 2011, your spindle speed. Your Z refer to your number of insert. Okay, in our case, we have 5 insert. Okay, so you want to calculate for the feed rate. So VF stand for feed rate. Then you can calculate. Then the output is 100 mm per minute. So this is your feed rate. So you can put the machine for feed rate. Then you know, so this is how we can use the table. Okay. So in your test, please remember the formula. Okay, the recommended for the solid carbide square and mill three fluid. So these are the configuration when you choose a cutting tool like a mill diameter. Then you have length of cut, total length, overall length. Sorry, length of cut refer to the cutting edges. Okay, start from your cutting region. Overall length 75. Shank. So shank will be overall length minus length of cut. For recommended setting for several operation in milling. For example, like you want to produce a slot milling, okay? You from this manufacturer, the recommended value for RPM and feed rate is okay. For example, depend on the diameter of your tool, 10.0. So these are the recommended value, okay? 5,800 and speed rate 1350. When you increase your diameters, you can see that the end will be reduced. So this is the formula because uh, V equal to pi dn. So n equal to V divided by pi d. So increase d and then n will be reduced. Okay, so AP stand for the axial depth cut. Recommended here in this situation is equivalent to 1 time of your diameter of your cutting tool. Diameter 10, so AP will be equal to 10. So this AP and AE is for the width of cut or radial depth of cut. So you can reduce to 0.1 or 10% of your diameter. So diameter 10, so this means your radial of cut or width of cut is 1.0. Okay, for the side milling, recommended similar. Okay, so please exercise, trying to practice this example. So this is our case study that in 3D milling using ball nose and mill. The first step is we do roughing, this setting for roughing, and then we do a semi-finish, and then finally we have finishing using scallop. So total machine time is 30 minutes. So as you can see for the finishing, you have to increase your spinner speed, okay, and then slightly reduce your feed rate. And we have a step over or width of cut, which is very small, 0.2 mm, to ensure that we have a mirror finishing. These are example of we have a pressing operation, pressing operation. Okay. These are the our wise. We model our wise. So, as you can see, and then we have a parallel bar, rest, okay, on the on top of your wise, okay. And then you have your side milling. So this is side milling operation. So make sure the yellow one is your cutting flutes. So the amount of the edges that are cut for the um, side milling, you can maximize, you can fully utilize your length of flutes. For example, this, okay, you're using 16.0 mm, so we go down until 16 mm. You can maximize. However, when you maximize the radial or width of cut, then you have to, oh sorry, when you maximize your axial depth of cut, then you have to reduce your axial. So you have to uh, play around or to balance between axial and radial. Axial high, then radial will be low. AP high, AE will be low. Okay, so this is two path. First to be approaching your piece and then goes down without any cutting, and then they're entering, okay, start cutting, okay, and then move to the side, move to the side, okay, and then finish. So we have a remaining. Please ensure that we have apply a safety height to prevent any collision with the wires. So I have a clearance for 2 mm, okay, 2 mm between top of the wires and the 2 mm clearance. Okay, so normally modeling, when you model properly, you won't have any collision. And then you have your uh, slot operation. So also in this case, I want to fully utilize my depth, axial depth cut. So I will make sure that I will use maximize the P, and then we will reduce the axial. So this will be ensure more efficient cutting. Okay. So width of cut is 0.1 or 1% or 10%. One, sorry, 1.0, 10%. Okay. I think that's all I finished on the chapter 3. Just a quick revision on this. So thank you very much for uh, watching my video. So hopefully we can see you again. Assalamualaikum warahmatullahi wabarakatuh.